at least 10 orders of magnitude have been gained in many domains when you replaced the light of classical lamp by laser light. And I would like to review all the progress. In a classical light source like the sun or a lamp, a spectral lamp, the atoms emit independently from each other radiation which have random direction, random phases, large dispersion in frequencies. And on the other hand, if you use laser light, as you know, now you have a light in which all the atoms emit in step radiation in the same direction, it can be with the same polarization, with the same frequency, and with a well-conserved phase. You can use powerful lasers not to heat matter, but you can use this light to cool down matter. If your laser beam is going in one direction and falling on an atom going in the opposite direction, by absorbing and re-emitting photons, the atoms can be cooled down to a very, very low velocity, even stopped in its path, and you can use laser light to trap atoms. And in this way, you can achieve extremely low temperatures, temperature of the order of micro-Kelvin or nano-Kelvin. At this temperature, the atoms move very slowly, and since they are very slow, they have very long de Broglie wavelengths. If you take into account the quantum nature of the atoms, you can reach temperatures for which the waves of neighboring atoms overlap with each other, and then you have a phase transition to a new state of quantum matter called a Bose-Einstein condensate if you work with bosons. And these Bose-Einstein condensates were predicted by Einstein again, and it took 75 years to observe them in the lab. The other interesting property is extremely high stability of laser light beams, which can oscillate, the electromagnetic field oscillates without skipping a single bit, propagating over hundreds of thousands or millions of kilometers. You can have this coherence, time coherence is extremely important in spectroscopy for interferometry. What we do is called cavity QED, but it's very closely related to ion trap physics, because in both cases what we are doing is interrogating single particles in vivo. By in vivo, I mean that we don't destroy the particles that we observe. We look at what happens to them. Previously, for example, in accelerator physics, or in the photoelectric effect, the particles that you detect are destroyed. And what you see is what happened before, but it's a kind of remnant of the evolution. Here, we do it in vivo, that is, we keep observing the system as we manipulate it. So I just show you here very quickly the kind of experiments that we were doing in Paris. We have a cavity which is made of two highly reflecting mirrors. Microwave photons can be stored in this cavity and stay in this cavity for a long time. You see the photons are trapped for more than a tenth of a second, which means that they bounce billions of times between the two mirrors before escaping or before being absorbed. And we send through the cavity single Rydberg atom. A Rydberg atom is an atom in which an electron has been brought to a very large orbital size, and the atoms are crossing the cavity one by one. They couple to the field in the cavity, and we measure them downstream, so we extract information from the field. There is a permanent dialogue between basic science and instruments and applications. Everything starts by the observation of nature, for example, the strange properties of light. It leads to theoretical models, quantum physics and relativity. This predicts new effects, like the laser, for instance, and the laser gives rise to new technologies that improve the precision of the instruments, which in turn allow us to make more precise observation, which will either confirm or falsify the theories. So it's a kind of what I call a virtuous circle. You go from observation, models, experiments, and checking the model again and again. And I think one big privilege we have as scientists is that we can appreciate these people. For someone who has no knowledge, no training in science, can appreciate the beauty of a piece of music by Mozart or Beethoven, can appreciate the beauty of a painting like Michelangelo or Leonardo da Vinci, but only a scientist who has at least a small training in science can appreciate the beauty of the work of someone like Galileo or Einstein. And I think this is a big privilege that we have. But you have also to be aware of the fact that this privilege comes with a cost. And the cost is that it's not an easy life. You have to get a position, you have to get the trust of the people who give you the position, you have to look for money, and so that's all what I can say. I say you have to find what you really like, and you have to have an idea of in which field you think you will be able to contribute and which field you think is important to work on. I guess you have all the scientists have the same kind of problems. They have to find what is their interest in, and the more you learn, the more precise can be your ideas about what you want to do, because you discover things. What you have to be careful about is also to understand that you don't need to know everything. You just need to know what is the path that you want to follow and in which you want to acquire new knowledge. The problem is that there are so much has been already done that you might feel overwhelmed by all the knowledge which has been acquired before you. And if you are inhibited by that, it's not good. I remember that when I went for my postdoc, I went in California and Stanford University, and I had as an advisor, as postdoc, Arthur Shallow, who got a Nobel Prize for laser spectroscopy. And he used to say exactly that to young scientists. He told them, you don't have to be impressed by all what has been done before you. You don't need to know everything. You just need to know one thing that the others don't know, which is easy to say, but not so easy to do, you understand? I'm well aware of.